Hello everyone. In this lecture, we are going to discuss about the central limit theorem and its use in construction management. We need to learn this only because it is the foundation behind the method of PERT, which is program evaluation and review technique. So it is just a different level of construction management above CPM, which is critical path method. So as we have discussed in the previous lecture, in this PERT method or program evaluation and review technique method, we use probabilistic estimate of time or durations of different activities and the project. So for that, this central limit theorem is important to understand. So let's have a look here. So there are random and non-random variables. So a random variable is generally assumed to be normally distributed. So by normal distribution, you can say that a variable will be following a distribution like this. However, if it is not normally distributed, that means some other factor is making it, suppose, skewed to this direction or skewed to the other direction. Sometimes some other distributions may also be observed. Suppose this is a fairly uniform distribution. A perfectly uniform distribution will be a rectangular distribution. Sometimes the distributions may be like this, where most of the population stack up at the extremes and few portion of the population will be in the middle, and so on. But if a variable is truly random, in that case it will follow this normal distribution. Now let's have a look at some examples. So for that, let's take a simple example of tests scored by different people in a certain test. So let's take this example where we have 25 marks, and out of that, so these are various students and their marks. So if you look closely at this table, you'll see that most of the students are scoring in the mid range. A few of them are scoring very low, but a few of them are also scoring high. And therefore, if we find out, or if we simply group them, suppose from 0 to 5, how many people are scoring, that means 4 people have scored very low in the range of 0 to 5, then 9 people are scoring within 5 to 10 range, then 18 people are scoring 10 to 15 range, 13 people are scoring 15 to 20, and 4 people have scored 20 to 25, that means in the high range. So if we put this graph, then it will look something like this. So here it is following a normal distribution. If we try to plot a graph like this, it resembles a normal distribution approximately. If the sample size is large enough, here we have only counted maybe 48 or 50 students, but if it is suppose 1000 students, then this distribution will be even closer to a perfect normal distribution, and instead of like this, it would be something like this, which is a better representation of a normal distribution. Now here, these are some random samples. I'll tell you why we are taking random samples. So to select random samples, there are some Excel formulas that I've used. I'll leave the link for that, the web page from where I got the formulas of how to select random samples from a given population. By population, I mean all the marks scored by these 48 students, or these 48 students, and from them I am selecting in random a sample of 4. So these 4 people, these 4 marks are listed somewhere in this population. So 15, maybe this 15, we don't know which 15, another 15, maybe some other guy also got 15, so this is 15, then 4, it may be somewhere here, suppose this is 4 marks, and 2, the last mark 2, and that is scored by somebody, suppose this guy, the last one. So then this is another sample of 4. So these samples we are collecting from this actual population of 48. So we are picking in random 4 samples. So if we do that enough number of times, we'll have a large number of samples which will cover the entire population. So these are groups of 4 samples, so it is about 12 samples. Then these are another set of 12 samples, and in these cells I have put the average of each of these samples. So this 9 is average of these 4 values. See, whenever I make some change in the sheet, it generates another random sample. So earlier it was 15, 15, 4, 2. Now it has become 18, 6, 10.5, 14, and so on. So it changes every time I make any change or try to save the Excel sheet. So you see, every time it is taking random samples. So this cell is representing the average of this, then this cell is representing average of these 4 values, then this cell is representing average of these 4 values, and so on. So we have large number of samples. The sample size is 4 and we have taken 24 samples. Now if we take these means or the averages of samples and then find what will be the distribution, as you can see in this, we have grouped them from 0 to 5, 5 to 10, 10 to 15, and so on. So we got this kind of a distribution. Now if we take the mean of these samples, so these are counting the values from 0 to 5, 5 to 10, 10 to 15, and so on. So in that case, we'll see that the mean is also normally distributed, kind of normally distributed. It may not be a perfect normal distribution, but it looks somewhat like a normal distribution. So if I save it again, it will generate another set of random samples. You'll see that each time, although the distribution is slightly different, but it still resembles a normal distribution like this. Now that's not so surprising because the original population itself was normally distributed, almost normally distributed. But there is a surprising thing that even if this original population is not normally distributed, that means students are not getting not less students are getting very low and very high marks and more students are getting average marks. It may be other way around also, where in a very difficult test most people will score less marks and a very few people will score high marks. So let's take another example. So this is another sheet where I have plotted different marks now. So let's say this is a very difficult test. The question paper was very difficult, and therefore most people scored very less marks. You see, most people are scoring in the single digits, and very few people are scoring above in double digits and above 20. So in that case, if we calculate these ranges 0 to 5, 5 to 10, 10 to 15, then we are saying that a large number of students have got very less marks, 0 to 5 and 5 to 10. Only one student got more than 20 or 20, and then 10 to 15 and 15 to 20 ranges again slightly smaller. So if we look at this distribution, here you can see that this distribution is not normal, and it is actually skewed towards the lower side, towards the lower values. Now again, if we take samples similar to the previous example, where these are samples of size 4, so we are taking random, we are picking up in random 4 scores out of these 48 scores and taking the average here. Again, we are taking 4 scores and taking the average here, and so on. So we have taken about 24 samples of size 4 and place the averages here. And when we count the averages or the means, they will be in this range. So the averages will be having a range like this, less than 0, obviously 0. From 0 to 5, there are 14 people. From 5 to 10, there are 22 people. From 10 to 15, 16. From 15 to 20, 7, and so on. And 20 to 25, only 1%. So these are the averages, not the actual population. The actual population, as you see, it was not normally distributed. It was skewed to the left, towards the lower values. But the mean, if we look at the distribution of the mean, you see this distribution is a graph of these values. Now this distribution has become a normal distribution, or close to a normal distribution. Not a perfect normal distribution, but it has resembled a normal distribution, even though the original population was not normally distributed. So this is a trick. It's a surprising thing, but we are going to use it as a trick for our PERT analysis, that is program evaluation and review technique. So even if we take other random samples, so when I click save here, it will generate a different set of random samples. So every time I save, it will generate different random samples, but every time although this one, the original population is remaining the same, it is skewed to the left, the distribution of the means is still trying to remain close to normal distribution. So we can try with different random samples. Every time it will be close to a normal distribution, and so on. So we can try the same thing with another kind of distribution. Suppose it is a very easy test, so this kind of a test. So here also, in this case, most of the people are scoring, suppose, more than 15 or 20. Very few people are scoring less than 10 or 5. So in this case, the distribution is skewed to the left or to the higher values. But even then, if we again take this kind of random samples and try to find out their distribution, even now we are going to see that it is kind of normally distributed, no matter how many times we take the random samples like this. It will be even a better or perfect normal distribution if we had a very large population, suppose 1,000 or 10,000 students, but right now we only have 48 students, so therefore it is slightly having these kind of sometimes double peaks and sometimes skewed to one or other direction. But for a very large population size, it will be very close or a perfect normal distribution. Even if we take a uniform distribution, that means the marks are distributed very evenly. Suppose 9 students got 0 to 5 marks, again 9 students got in the range 5 to 10 marks, 10 students got in the range 10 to 15, 9 students got 15 to 20, and 11 got 20 to 25. So it's a fairly uniform distribution. Even then, the distribution of the means of the samples is still normally distributed. As you can see, after random samples, it is coming as normal distribution. Then let's take a very weird kind of distribution, which is not generally seen, but just for the sake of example, we are taking this, where most people are scoring either very less or very high, and very few people are scoring in between, which generally doesn't happen, but it may be a case in some situations, in some extreme situations. But even then, it doesn't matter what distribution the actual original population is. When we take the samples and their means, the means always tend to be normally distributed. And as you can see, at random, after different random samples, it still remains close to a normal distribution. So this is one trick that we are going to use. It's a phenomenon actually, and we are going to use it as a trick for our construction management purposes. But let's see how it is going to help us. So let's try to articulate the whole thing. The sample mean of any distribution is normally distributed. So that's what we have learned from the previous examples. To be more precise, if we take samples from a population which may or may not be normally distributed, as we have seen, the original populations were sometimes normally distributed, sometimes not, and compute the mean of the samples, the means are always normally distributed. They tend to be normally distributed. And if we try to be even more precise, then we can write it as, if from a population we take large number of random samples, so the number of samples will have to be large, which themselves are large enough. So this means that in our examples we took samples of size 4. So each sample was only having 4 of the values from the original population. But if we take a large population, suppose 10 or 20 or 30, in that case the mean of the samples will be normally distributed, and it will be almost a perfect normal distribution if we take a large enough sample and a large number of samples. So both of them are important. The sample itself has to be large, and the number of samples will also have to be large. In that case, we will get a very good, perfect, normal distribution like this. In our case, as you have seen in different trials, sometimes we got this kind of distribution, sometimes we got this kind of distribution, but they still are close to the normal distribution, unlike the original distributions, which were like this or sometimes like this. So it doesn't matter what the original distribution was. Now, why is it necessary to learn in the context of construction management? So the expected duration of an activity is represented by the mean or the simple average duration of the activity if it was repeated a number of times. That means suppose an activity artwork, it may be distributed like this, where most of the times it will be completed within a short time, but sometimes it may take a very long time. But it doesn't matter. We are not worried about this distribution, because the expected time or expected duration of an activity, we are defining it as the mean or the simple average. So in that case, we'll calculate the mean somewhere around here. The mean itself, if we take large enough samples, will be normally distributed like this. So the mean duration is shown to be normally distributed by central limit theorem, as we have learned in the previous examples. And expected total duration of the project is sum of expected durations of all critical activities. So we have defined the term expected duration as the mean. So therefore, we are only going to deal with the normal distributions, because the mean is always normally distributed. And since these expected durations of the individual activities are normally distributed, therefore the total duration will also be normally distributed. The total duration is normally distributed. So if you take a simple example, suppose this is a activity network where, as you can see, this would be the critical path, and these are the expected durations: 4 days, 5 days, and 4 days, which will be the mean or the mean of the distribution, or the expected duration of these various activities. And therefore finally, if we want to find out the total duration, it will be also a normal distribution, because it is sum of a series of normal distributions. So here, after we get the normal distribution for the total duration of the activity of the project, then we can commit to our client that this much is the probability that this project will be completed within these many days. Suppose this value is 25, then we'll have to find out how much is this area of this distribution. Suppose this is about 35%. That means, as you know, the total area under a normal distribution is always equal to 1 or a unity, or we can say 100%. So this area is suppose 0.35 or 35%. So if somebody asks what is the probability that you are going to complete this whole project within 25 days, that means this value, we can say that it is 35% probability. But what is the probability that you are going to complete it within, suppose 42 days? So in that case, we'll be calculating this entire area up to this. So this area will be around, suppose 97%. So we can say or commit that or promise that we'll be completing, the probability of completion within 42 days is 97%. And if we consider this date, which is the most pessimistic estimate, that means when everything goes wrong, even then we'll be completing, suppose this day is 48 days. So within 48 days, we can say that it will be 100% complete. There is 100% probability that it will not take more than 48 days. However, generally we do not say 100%. We stop at suppose 99.9% or something like that. So in PERT method, which we are going to learn in the next lecture, which is called program evaluation and review technique. So there will not commit that this will be completed in 25 days or 30 days, but will give them the probability of completion within a certain day or within a certain duration. So that's all for this description of and demonstration of this central limit theorem, how it works. You can look for the proof of this theorem, the central limit theorem, but here we have only verified using an example, but you can look for the proof. It's actually very difficult mathematically, and we don't want to deal with those kind of complex statistical analysis. So now we only know that this central limit theorem exists and how we can use it in our project management course. So that's all for this lecture. Thank you.